Hello, and thank you for joining me. You're here with data science teacher Brandon, and we are going to do our second level NLP, or level number two, NLP multi-class prediction. So NLP is really tricky, and to get really good NLP models, we'll have to get much more complex than we're going to do today. But this is a good set. This is a very tricky set for the poem classification. So it's very, very hard to get a good score on this one. And it's good to practice on. So we're going to do some different things that we've probably seen, but that work good in different places in NLP. Okay, it's a little bit more advanced than our first model, but again, it can work in different situations. So there's so many different architectures. It's just good to practice really as many as we can. Okay. So let's start off by importing our standards. So just importing the standard data science libraries. Today we're going to be building a neural network. So we're working with TensorFlow as TF. We're going to use some machine learning stuff from the machine learning library. So from sklearn.train test split, or import train test split. Let's call that right. And then import. So we're going to use it for from this as well for label and color. And so this is we're going to need to convert our targets into integers, into numbers. And so this is what will allow us to do that. And then save it if we wanted to be able to pull them back out later on. Okay? And so here we're going to also do plot the confusion matrix, and we'll look at plotting our confusion matrix for a multi-class prediction, because we tend to find that I personally find that your models are very sensitive. Deep learning models specifically are very sensitive to uh, the balance in your classes. And so with a slight imbalance, you'll be able to see what just a slight imbalance does. And so one of the things that we could do, in another class in a higher level is look at resampling this and look at trying to balance out the classes. Okay. So what we're going to do here, so we have train test split, and then what we're going to do is we're going to import and natural language TK, natural language toolkit, so NLTK, and we're also going to import just for a couple of pre-processing things. Okay, and the data is in my GitHub reservoir, so you can just download it from my GitHub and get access to it. Okay. And then so what we're going to do is wait for all of the libraries. TensorFlow is a big library, so we're waiting for it to upload. And then we're going to upload the data. First thing I'm going to do is check the shape, and then the shape of my test. Train data set, test data set. So here we go. The DF head is going to be, just looking at this, we can see we have music, genre, and so just two columns, which is pretty typical in an NLP data set. So we're going to look at null values. So df.isNull.Sun. We have 4 null values. So we don't really, it'd be kind of hard to replace this with anything. It's a poem. There's no really filling a poem. So we're just going to drop those rows. So the next one, we'll print out the shape. We're going to get the df.drop NA, and then we're going to assign that to df, so it'd be returning a data frame without, and drop NA by default just drops any row that has a null value, so we're just going to drop those rows. Okay, so we got 4 less rows now. Okay, so perfect. Let's inspect the balance in between our classes next. So value underscore counts. And I want to do plots. So we counted the values, it counted each of the genres in our data set, and you can see here we have a lot less representation of affection. And we'll see, not to be a surprise, but we're not anywhere near as good at predicting affection compared to the others. We actually almost kind of avoid predicting affection. And so this is one thing that we'll, as we expand or make our workflows more complex, something to pay attention to is the balance in your classes when you're doing specifically multi-class prediction. It can matter if you only have 2, I guess, but it matters really significantly when you have a multi-class problem. Okay, so here what we're going to do, we're just to inspect what our poems are. So I'm just going to use iLock and get out the first one. So you can see we have some of these things, which is good. So it's really just a good idea to inspect the text and see it, it is what it is. We have to do some EDA. It's a little bit less interesting, I guess, in some senses than a spreadsheet. There's a lot more you can do in a spreadsheet, but really, really valuable to understand. So this is, I did some research. I had never seen this before. This is a special character. It is not, it's kind of like a line break, which is, you can think in a poem, they would have line breaks. So it took actually a little bit of tricks to do, to get rid of. Okay? So we're doing this, and we're going to try and remove the thing, so we can see we have some of our poems right here. So what we can see here is we're going to use, well, we're going to try this first. So we're going to find out that it does not happen. So what I thought this would work, this would be kind of the standard way you would do it, just putting an R in front of your string. This means this is a regex string, and ignore the special regex character, this character right here. Ignore the fact that it's a special regex slash, and it means something special in regex. So ignore that, and we should be able to replace then. But when I look at it, still it looks like it didn't replace. So I was able to find this on the internet. So it was string dot split dot string dot join. So the reason that this works is it splits on the white space, what this technically is. Then it's going to string, and then it's going to join that afterwards. It's going to add a space in the middle of this. Okay. And so there. So we join our data set, we join it on that, and go through. Gives us a nice little thing there. Now what we find is another good idea. So I just wanted to inspect it by, it was a little bit tricky to figure out a way to solve it. The internet always has a solution. So we got rid of the special character, the line breaks, and the special line breaks. Okay. So we're going to this one. It's a good idea just to inspect it by, you know, each poem type, right? So I wanted to see death, music, environment, and affection, and really just see if I could notice anything special about anything particular to one of those poems that might be interesting. So nothing really special in music. What I can see here is in death. In the second one, death, you can see we have these stuck together words where there's just, it's really just kind of a line break. And you'll find this happens quite a bit in this data set. So I just noticed this right here. So I noticed this and I made notes of this. This could take a little while to figure out or to do all of them. And to get the best score, you would probably want to. I did a few for us today to show how it's done. To do this in more depth would require a lot. So it's just string dot replace, taking what I had and then what I want to do. So just adding the white space. It's kind of a tedious step, but this is typical, I guess, of NLP. Is there's always, well, not always, there usually is a little bit of a tedious step. And that just has to do with kind of the formatting of this, but we're just getting ready at making sure that this is two separate words. Okay. So going through some editing of that. Also, to make sure the characters are the same, we're going to go string dot lower and make sure all of the characters are now lowercase, just to make sure that we don't have, it treats a capital and a lowercase like the same way. Okay, so we're going to do stop words, get rid of those really unimportant words here. So we're going to go corpus dot stop words dot words. And then we're going to do English words because we're dealing with English text, and we're going to go replace. If we're doing a list of values here, we need to do replace instead of dot string dot replace. It's just dot replace. Okay? And so once there, and just notice here we downloaded the data set first, then we have to do the steps of NLP dot download to get the stop words, and then we're getting the stop words right here. To do punctuation, to help fix this problem where lots of the punctuation was right around or was kind of the squished together part with the line break. So if we just change this to a space, we'll have two separate words, and we're going to remove the punctuation anyways. So instead of punctuation no space like I did here for the stop words, I'm going to do space. So there's nothing really different. So that's why I did this separately. Okay, there we go. And here what we're going to do is replace this as well. Please. And then I'm going to assign my train test bed. So I find it easier, not at this level, but as we get to more advanced levels, your model has inputs and outputs, and it might have many inputs and many outputs. Not just different columns, but different data. You might have pictures and words, spreadsheets. You can have really a lot of different things. They're very flexible in what they can handle. And so I think it's good. It's just good to get in this habit. So, and to help us think through this, so I'm going to say input and output. It's going to be INPT for input, OT, PT. So just output without any vowels except for the first letter. And I'm going to use our train test split to do the train test split of this. And here we have, instead of the number of words or max words that we're going to do in our tokenizer, it's going to be 500. because there was a lot of words here, but I played around with this a lot, but I found that it worked a little bit better having a smaller number. This is a tricky data set to get even a moderately good prediction because poems are kind of, how would you say, the artsy part of words. They're really used in a beautiful way, I guess you'd say, but in a kind of abstract way a lot of the time. So this is very hard for a model to do. So, but what we're going to do is, and what I found is it's just better to have a smaller number of maximum words because there's probably lots of words that only appear one time in the whole data set, or even in the fonts with how writers write. Okay, anyways, so here we're going to do tokenizer. So we're going to go tokenizer equals tf.keras dot preprocessing dot text dot token, capital T tokenizer. Okay. Our num words is equal to a 500. Our filter is equal to these, kind of getting rid of some of the special characters and stuff. Let's writing those out. And any words that it doesn't see is going to be the out of vocabulary token, which is just going to be this kind of standard. So I'm going to do that. I'm going to then fit on text. Fit on text, plural right there. And then I'm going to get my word index to understand how many words I have. So word underscore index. And I'm going to go right here. Let's go len of the word index. And in total, it's 7,658 words. Then the next one, we're going to go text to sequences. Okay, so we're going to go tokenize text to sequences, not text to image, text to sequences, text to sequences. And do that again on the bottom one here. It's text to sequences for both of these. Okay, so this is going to change our words into sequences. It's still not going to be the same size, so we're going to have to pad it afterwards, but we need to know what the maximum length of this is first. So it's a good practice doing a list comprehension. So we're going to get the maximum of 4s in input. So for the values in our input, we're going to iterate through the rows, and we're going to get the length of each row, and this basically is going to turn into a list when it comes out. So we're going to get the max value here of this list of lengths of the input value. It's really quick and easy, and it's nice that we do this in list comprehension because then we just put this inside the max function. In the next one, we're going to pad our sequences so that they're all the same length. Right? So this is where we've got max length, and here we're going to do utils and then pad underscore sequences. We're going to go padding equals padding pre, and max length equals to max underscore. Max length, max underscore length, so we're going to pad our sequences. Okay? We're going to do label encoder because we need to do linear algebra on our classes. So even it still needs to be, it can't be in text. It needs to be in number form for the pre-processing, just for to work with TensorFlow. Okay, so we're going to do label encoder dot fit. We're going to fit on the output, so our y variable, what we're trying to predict. Spell fit correctly. And then we're going to assign that to y or le, label encoder, an object, and we're going to transform our output, and then assign it to output. Transform for purpose. Now our transform is going to turn from strings into 1, 2, 3, 4. Well, 0, 1, 2, 3, 4. Python in 1. Okay. So we would need to do this first if we were going to do this step. We don't have to do this step because we can use a special version of categorical cross entropy. Categorical cross entropy. Okay, so categorical cross entropy, and this is not with sparse. So if we don't want to use this sparse version of this, we can do this first. So this is basically going to convert it into 4 columns, not just one column for the prediction. It'd be 4 columns of predictions, each one representing one of the targets, and the one with the highest value is considered our prediction. Okay, so that's how this works. This is our model will do this for us inside to be able to do the linear algebra, but we just need to know, be aware of this to get started. So we don't have to do this. We have our data set, our target in one column. If we want to use it in that form, if we don't want to do this manipulation first, We just have to make sure that we're using sparse and not just the standard one without sparse. Okay? So, and you'll see that in the next section right here. Okay, so first we're going to do our output. We're doing a multi-class prediction, so we're going to go tf.nn.softmax, softmax prediction. Our optimizers are going to be optimizers.atom, and then we're going to do dot losses, tf.keras.loss, losses, and here we're going to do sparse categorical cross entropy. Okay, so there's sparse and there's not sparse. Sparse is we're giving it one column, and categorical cross entropy would be if we had done this step right here. So just to show you what this is kind of, I found this very confusing. It's very different than it works in sklearn. Kind of does this stuff for you. We have to be a little bit more conscious of this. This does happen underneath the hood in sklearn, but you just don't have to deal with this. Just a little bit different, but just to kind of walk you through that stuff. Okay. So here we're going to define the architecture. Now we have some of the hyperparameters defined. We're going to define our architecture. And so first we're going to do tf.keras.layers.embeddings. So this is the big thing that we're doing today is the embeddings. Okay, so we're going to do 3 times the number of words. I had to experiment to figure out 3 times. It worked really well. It had something to do with this being a poem and kind of the abstract context of the words and kind of it's kind of more of a, they're complex. I guess we needed quite a few embeddings here. The embedding dimension is, we're setting this here. Sorry, embedding dimension, we should set this to 16. Or sorry, 128, I apologize, 128. And then what we want to do, so embedding number words times 3, which we have the numbers, we're going to do 128 for embedding dimension. Our input length is our max length that we used up above, that we got up above. And the next one, this is probably going to be different, is going to be a spatial dropout 1 dimension. This works well in the sense what it's going to do is make sure every character essentially has a 0.45% chance of being dropped. So it's not just going to be a value in this row has a chance of getting dropped. It's going to be, every single next value in the embedding has the same chance of being dropped. So this just works well with NLP. Okay, so in the next one, then we're going to do is we are going to do global average pooling 1 dimension. Okay, so global average pooling 1 dimension, and then we're going to flatten this. Predictions, capital F flatten, and then on our output layer, we're going to do a dense layer with 4 neurons and a softmax activation. Okay, here we're going to do loss equals LS, our loss up above, optimizer equals OPT up above, and our metrics are going to be accuracy. Okay. We're going to fit this model, and then we're going to go say epochs EPS, which is 9. I find a few more might be good, but it really, you don't want to train NLP too much because it's, so let's just say, sorry, validation data equals this input and output here. But I found with NLP, you really don't want to train it too much. It's very easy to overfit, and you'll see we're even getting some overfit from 9. So this is probably going to take a while, not too bad to train. And we'll go through here. So now this is done, we're going to plot, and we're going to plot the history. So notice when I fit this model, I assigned it to H. So I'm going to go pd.dataframe. I'm going to go H history object, h.history, and I'm going to plot that. Very easy way to plot the history of your. Let's see, you're coming down a little bit. We didn't train for very long. I think you'll see it's starting to change. If you train for a little bit more, you'll start to see that you get a lot of, how would you say? You start to get a lot of overfitting happening. And it hasn't happened yet. At 9, it won't, but maybe like 15 or so, you'll probably start to see. So here what we'll do is we'll predict from our model. We'll look at our confusion matrix. So predict for both of these. We're putting our inputs to get our output, train, predict, output, test, predict. So we'll run both of those. And what one of them looks like. This is what I was mentioning. We have, this is our target. This is our prediction right here. So what this is saying is it predicts 1, 2, 3, 4. So it was the most, had the highest one in here. So if we, what we're going to do is tf.argmax, and this is going to give us the position of the highest one. So our prediction is the second position, which is related to position number 1, Python indexing 0, 1, 2, 3, and our final prediction is this. So this is what sklearn does as well underneath the hood, but then we'll kind of summarize this for you afterwards. But we would have to do df.argmax. We're going to do axis equals 1 because that's just going to go across the row, right? So we're going to find now the maximum value across the row, and that's going to be our predictions. Right? This will fit really well with label encoder, and this is just going to be done alphabetically. So you can see here, if I put this as it was into a confusion matrix, we're getting an error. It just doesn't really make sense like this because we need this in the one-dimensional format instead of this multi-dimensional individual column for each prediction. Okay. So what we're going to do here, we'll go confusion underscore matrix, and then we'll go tf.argmax, okay. And then access equals 1. Yeah, we got a confusion matrix. We got to spell argmax correct, and then we got our confusion matrix. Okay. From there, what we're going to do is data frame, and we're going to put CM inside, which is just going to like this. We're going to give it the value. So this is going to work alphabetically. So it's just easy in this sense. I did this in alphabetical, and we'll do depth rate. So we'll do this one here, and we're going to spell data frame correctly. Data farm. And there we go. Yes, and you can see here, we didn't really get any predictions for affection. That was a lot. We noticed as well that there was not a lot of values for this row. Oops, I gotta fix this one right here. So making the CM right here. Okay, so now we made our CM. So just to show you what it looks like, I'm going to assign this to df underscore CM, and I'm going to put this into a heat map. And I'm going to do that. And then true crest title. Okay. So just to do this all together, so that was for the train data set, we got our train confusion matrix. Now if we want to do our confusion matrix for our test set, so confusion matrix. We're going to put in our test set, our test predictions, and inside argmax. And then we're going to go df.data, pd.data frame, and put in our confusion matrix. Our titles, we're going to put this into a heat map. And then we're going to put the title as test confusion matrix. Okay, and there we go. And you can see here really the balance in how bad our predictions were greatly affected by the fact that we were never predicting affection. And that's one of the main reasons is the fact that it was undersampled comparative. So it would be very hard to get this to above like an 80 prediction, very, very hard, but we should be able to increase our prediction simply by resampling. So we'll work on techniques like that in more advanced projects as we get to the more complex stuff. So thank you very much for joining me today, and I look forward to seeing you for the next NLP or computer vision or deep learning or data analysis project. Take care.